Welcome dear students. Today we are going to solve two very good questions from the Prescore test series in fluid mechanics. So this is the first question, and you see it is saying that there is a cubical block of side given and the density is given and it is floating in water and the dimensions of the base of the container are given. So we have to find the minimum work done by the external agent so that the block just gets submerged in water. That means this floating block we have to push so that this upper surface just gets submerged beside this water level. So let us start. Suppose this is the situation and here the block is floating like this. The density is given what? Its density is rho by 2 and the density of water is rho. So what can you say? How much length is initially submerged under the water? Let us say this is what? This is h. Okay. This one is h. It is submerged under the water. So what we can write by the buoyancy? What is the weight of the block? The weight is, its dimension is L. All the lengths are given as L and the dimensions of this one is also given, and it is, say, let us some A and B, or we will take its cross section as A. Okay, cross sectional area of the bottom we are taking as A. So what is happening that if you apply the buoyancy the force balance, then the weight force is what? Weight of the block is volume, that is L cube times its density rho by 2 G. This is equal to what? The buoyancy force. Buoyancy force is what? Whatever is submerged inside the water. That means what is the cross section of the base of the block? L square. Let us say H is submerged. So this is the volume submerged and the density of water is what? Rho, and it is G. So from here you get what? You get H is nothing but L by 2. That means in initial situation half of the length of the block is under the water. So this H is L by 2. Okay. Now let us mark this point, this half point, which is initially at the level of water. So we have marked it with a red paint light, let us say red paint line. Okay. And similarly the vessel we have marked with red paint at the initial water level. This is being done so as to identify the changes in the levels which are taking place during the push. So let us now push the block inside. Something like this. The block has been pushed and now the central line of the block is somewhere here, let us say. How much below it has gone down? Let us call it x. Okay. Now what do you think? Will the water level remain the same? No, because some volume has been occupied by this extra push of the block. So how much volume it has been occupied by the block? It is nothing but L square times x. L square is the base area of the block and x is the distance by which it has been pushed. That means this volume of water will be pushed upward, isn't it? On where is the scope to go up? Obviously in this part and in this part. So the water will rise up, something like this. And how can you calculate it? Let us say water has rised up by y. So you can find the y by balancing the volume of this part which has been pushed by this extra part which has come up. So let us try. L square x is the volume pushed by the block, volume of water pushed by the block, and it must be equal to the volume of water raised. So what is the volume of water raised? Area of cross section times y. But area of cross section must not include this area, because this area is the cross section of the block. So only this area and this area should be taken. What is that? It is nothing but A. A is the base area of the cylinder of this vessel. A minus L square times y. This is the relation between x and y. So from here we can write what? Y is equal to L square upon A minus L square times x. Let us call it alpha x, okay, because we don't want to write this complicated equation again and again. So alpha we have summarized it. Okay. Now y is equal to alpha x we will use. Y is equal to alpha times x. Okay. Now you see, had the water been up to this level, okay, had only this part been submerged, it was floating under equilibrium. But now this much extra part has been dipped. So some extra buoyancy force must be applied, and some extra force from the top is being applied so as to maintain it in equilibrium. So what should this extra force be? This force should be the buoyancy given by this extra submerged part, this extra submerged length, that is buoyancy given by x plus y of the submerged height. That means what you can say? You can say that F, external force, external agency which is applying this force, F should be what? V rho g. V is what? L square times x plus y, V rho of water, that is rho, times g. Okay, this is the force which is being applied by the external agency in order to keep it in equilibrium when it has been pushed down by distance x. Okay, so now you can write y as alpha x. So F is what? Nothing but L square x 1 plus alpha times rho g. See, we got force in terms of x, isn't it? Now it is very easy. What is the work done by the external force? dW. Suppose it is pushed further down by dx. Then what is the work done by the external agency during this time? dW is F dx. Now simply integrate from initial to final. So what you get? You get total work done is what? You just write it. L square 1 plus alpha rho g times x dx. Okay, now during placing the limits you should be careful. Okay, what is the initial limit? When the block was floating freely, when it was here, x was 0. So initially x was 0 and finally it is fully submerged. That means x plus y is covering up to this point. That means this total is L by 2. So x plus y is L by 2 in finally submerged case, just submerged case. So from here what you get x is equal to what? L upon twice of 1 plus alpha. This is the final limit. So here you put the limit what? L upon twice of 1 plus alpha. Okay. Now you simply solve it, you will get the answer. W is what? W is L square by 2 1 plus alpha rho g times square of this one. That means L square upon 4 1 plus alpha square. Okay. So now you simply solve it and you will very easily get the answer. 1 plus alpha cancels this one here, this one here. So it is nothing but rho g L to the power 4 upon 8 of 1 plus alpha. Okay. So if you put all the values, alpha is what? Alpha is this one. Alpha is L square upon A minus L square. So all the values are given. You know the L, you know the area of the base, so you know the alpha, and you know the density of water G and L. So everything if you put, then you get what? Work done is nothing but 6.75, which is the answer of the question. Okay. Similarly, let us see the next problem, which is this one. In this cylindrical tube has been taken, and initially this gap was filled. This gap was, blocked with our finger, and this was filled with water. Okay. Then it was inverted in a bigger vessel in such a way that the bottom part is up and the open part hides in the water. Now this small hole was opened, the finger was removed. So what happens? That the air rushes in, isn't it? Air will start rushing and this water starts falling down. So we have to find the velocity by which this water surface goes down. Let us see how we'll approach it. This is the situation. Okay. Here what is happening? Initially this was filled up to here and it was inverted and released. Now because as it is released, what is the pressure outside? It is PA. Okay, and what will happen? What do you think? Why the air will rush in? As this layer goes down, there a partial vacuum is being created in this part. Let us call the pressure here P. Definitely the P will be lower than PA, isn't it? P is lesser than PA, and because of this vacuum, this air flows from outer side to inner side, isn't it? Rushing it in. Let us say the flow velocity of air is what? It is V, capital V. So in the question, you see, it is given that you can assume the motion of the air as an incompressible fluid with density rho A, and the motion is streamline flow. That means you can consider the air as a fluid. Okay, so that means you can apply the Bernoulli's principle over here. So let us take a point here 1 and a point outside 2 and apply the Bernoulli's equation in between. So what you get what? P atmosphere minus P inside is what? Half rho air times V square. Capital V is the velocity of the air rushing in through the small hole. Okay, so this is first equation from Bernoulli's equation in the air. Now you see the pressure here is P, and we assume the density of air very small, so the pressure will remain almost constant throughout this chamber. That means at this point also we will take the pressure as what? P only. So here the pressure is again what? P. Same pressure here, same pressure here. Now what you do, you apply the Bernoulli equation in this part. Let us take this as point 1 and the exact surface over here, this as point 2. Okay. Now you apply Bernoulli's principle over here. What is the pressure over here? The pressure is P, same. So P plus what is the velocity? Let us say velocity of water surface is VW. P plus half rho water VW square plus rho W G H is the height is what? At 2. At 2. You see what is that pressure over here? Pressure is same, which is the outer same layer, because we know that at the same vertical level pressure remains the same. So here the pressure is atmosphere. So here also pressure will be atmosphere only. So let us write PA plus velocity is again same in the whole column, half rho W VW square. Okay. Now you see these two terms cancel out, and what we get PA minus P is equal to rho W GH. This is the second equation. Now you see 1 and 2, their LHS is the same, so RHS will be same. That means what you can write, half rho A V square is nothing but rho W GH. Now how to relate V and VW? VW is what? VW is the velocity of the surface of water and V is the velocity of the air. You see one thing, from the continuity equation, whatever is the rushing, volume which is coming here must be the volume which is expanding. That means what you can say, A1 V1 is equal to A2 V2, you should write. So A1 is what? A1 is pi small d square by 4, pi d square by 4. V is what? Pi capital D square by 4, pi capital D square by 4 times VW, isn't it? So here you get what? V is nothing but VW times capital D upon small d whole square, isn't it? You take V here and D will go down, and it will, now you put this in this equation. So what you get? You get half rho air VW square times D upon D raised to power 4 is equal to rho W GH. Now from here what you get? VW is twice of rho W GH upon rho A under root times D small d upon capital D square. So this is the velocity of water surface, and this is the answer. So I hope you liked the video, and if you have any doubts, questions, queries, then feel free to ask in the comments and I'll be happy to respond. Thank you.